In the name of God, the compassionate, the merciful. Engineering Plasticity course, Chapter 1, Introduction, Part 4. So far, we have talked about single crystal and plastic deformation in a single crystal. We showed that if we have a single crystal, this rod supposing is a single crystal, and if we suppose that a slip system is this, that is the slip plane, and that is the slip direction, and the normal to the slip plane makes an angle phi with the applied force, and the slip direction also makes an angle lambda with applied force, we can develop this equation. This equation, in fact, shows how slip occurs. Sigma is this. In fact, the applied load causes sigma, and sigma causes 2r. So if we suppose this is the slip system, that's how the slip occurs. If sigma reaches a certain value, 2r reaches a certain value, and a slip occurs. Now we have this certain value in here, tau CRSS, critical resolved shear stress. If tau r reaches this value, which typically is between 10 to minus 4 gigapascal to 10 to minus 2 gigapascal, then if this value reaches that, then slip occurs. It means that sigma or F must increase. Sigma must increase because lambda and phi are constant. The slip system is certain geometrical position. So this is constant, which is called the Schmidt factor, and depends on the crystal. Now this value, F divided by A also is constant because it's the cross-sectional area. So F is the only changing thing in here, because F is the applied force, is the tensile force. If we increase F, this increases, tau r increases, and if F is increased enough, then tau r reaches that value and a slip occurs. Now, we're going to show you here some special conditions. For instance, if lambda is 90, this slip direction is perpendicular to the applied force. If the slip direction is perpendicular to the applied force, then tau r is 0. Resolved shear stress becomes 0. No resolved shear stress. Now, if this is another special condition, if lambda is 45 and phi is 45, then cos 45 and cos 45 are 1 over root 2, and then it becomes sigma over 2. Tau r is sigma over 2. This is what we see in ductile materials. Now here again, if phi is 90, okay, that means the slip plane is oriented such that phi becomes 90. If that happens, again cos 90 is 0 and tau r is 0. Okay, so these are the extreme conditions shown in here. Tau max happens at lambda equal to phi equal to 45 degree. Of course, phi and lambda are independent of each other, and they could be 45, both of them could become 45. Due to this equation, cos lambda cos phi, we must have 45 degree in order to have maximum value for tau r. Otherwise, it would be less. Okay. Again, here we go back to the tensile test of a single crystal. Okay, this is the single crystal. This is the direction of force, and that's how the slip occurs and how the extension occurs. In other words, when we apply the tensile stress, the tensile force, in fact, the material doesn't extend in that way. It moves in that way. It doesn't move in that way. It seems to be moving that way, but in fact, it is moving like that. Okay, these are the shear stresses, right? Now here is a simple example, the formation of a single crystal. Will the single crystal yield? We want to know if this single crystal yields. If not, what stress is needed? Okay, what single crystal? This single crystal, okay? This is a single crystal. The slip system is given. That's the slip direction. Lambda is 35 degree and phi is 60 degree. You see, phi plus lambda here is 95. So it's not necessarily 90. And there is applied stress 6,500 psi, okay, pound per square inch, 6,500 pounds per square inch. And for this condition, the problem has asked us, will the single crystal yield? Okay, we can use the Schmidt factor and Schmidt equation to calculate the yield stress. Now, how could we do this? If we must have this number, critical resolved shear stress. Critical resolved shear stress could be obtained experimentally from experiment carried out on the crystals. Okay, so we must have that number, 3,000 pounds per square inch psi. Now then, let's see if our resolved shear stress reaches this number. We can calculate resolved shear stress because we have all these numbers. Right then, we'll do that. Now, sigma is 6,500, lambda is 35 degrees, phi is 60 degrees. So we substitute all these numbers here and we get 2,662 psi for the resolved shear stress, which is smaller than this 3,000 psi critical resolved shear stress, which means that it does not yield. Okay, because yielding is equivalent to the slipping. When the slip does not occur, no yielding, because plastic deformation is basically due to shear stresses. Plastic deformation is basically due to slip of the crystals. Okay? If there is no slip, there is no plastic deformation. So the only reason we have plastic deformation is because of shear stresses and because of the slip which occurs in the atomic planes, right? So because this tau r resolved shear stress does not reach the critical value, no slip occurs here, no slip, no yield. Okay, then in the second part it says if not, if yielding does not occur, what stress is needed to yield, for the yield to occur? We can calculate that. So the applied stress of 6,500 psi will not cause the crystal to yield. Okay, then second part, what will cause it to yield? We put tau r equal to tau critical resolved shear stress 3,000. That was the number given to us. So we put 3000 psi over here and calculate sigma y. Lambda and phi were given like before, and multiplication of this is 0.41. 0.41 sigma equals to this. The reason I have put y here because I have put this to equal to 3000. I know that if tau r is equal to 3000, the yield occurs. So I have put instead of sigma y. And then sigma y is calculated as 7325 psi, which is much more than the value which we obtained before. Okay, it was 2662. We need 7325 psi for the yield to occur. So sigma must be greater or equal to sigma y in order for the material to yield or plastic deformation to occur. So you can see we can use crystal plasticity to calculate yield stress, to see which planes and which directions are critical and slip occurs at which directions and planes. Right. Let me come back to polycrystal materials because I told you before that I will explain some of the maybe ambiguities that were raised when we were talking about single crystals. Now, how is the plastic behavior of a polycrystal? This was another question we asked. Okay, now these are, as you can see, the directions of these crystals here are very clear, and these are the boundaries. The boundaries between different crystals are very clear. This is a real picture. Okay, real picture. That is the reference. Now, we know that on a single crystal how a slip occurs. In a single crystal, because all the planes and directions are parallel to each other, we have a certain plane and a certain direction on which the slip occurs. It's very clear. But in a polycrystalline, it's not like that. The reason I say certain plane is that, you see, because on this plane and this direction, a slip occurs. If we change the plane and direction, we don't get this number, and then we need a higher stress. So that's why for this plane and this direction, a slip occurs, because the force reaches a certain value that occurs on this plane and this direction. If we increase the force more than this, if we increase the force more than this, so that we get sigma, a larger number for sigma, what happens? What happens is this, that certain direction and certain plane, a slip occurs at a certain value of sigma. Now, if we go to the another crystal, obviously in this crystal, because it is oriented in such a way that a certain plane and certain direction, the stress becomes maximum, and tau r becomes equal to tau critical result shear stress, and a slip occurs. This crystal yields, but this crystal doesn't yield. When does this yield? If the tension goes up, if the stress goes up, if the force goes up, then we reach a certain value of tau r on a certain plane and certain direction in this crystal, which reaches the value of tau, critical result shear stress, and then slip occurs in another crystal. So in this polycrystalline material, it's like this. When you increase the stress, the result shear stress in one of these crystals, which have a favorable plane and direction, reach a maximum and yield occurs in that crystal. And then the next crystal may be this one, which has a less favorable plane and direction. Then as the force increases, yielding occurs here. And then in another crystal which is less favorable than this and that, then in this less favorable plane and direction, slip occurs. So as the force increases, yielding occurs in one crystal, then another one, and that's how the yielding in polycrystalline materials occurs. Many of these crystals must yield so that the material yields. Okay, I have spoken here that the stronger grain boundary pin deformation. One of the things that happens here are these boundaries which hinder the plastic deformation. Slip planes and directions change from one crystal to another, obviously. Tau R will vary one crystal to another. The crystal with the largest tau R yields first. Other less favorably oriented crystals yield later. This is the explanation that I have just presented for you. So the plastic deformation in a single crystal, the plastic deformation in a polycrystal happen in this way, and it's all to do with the slip system. Okay, slip plane plus slip direction, lambda and phi. These two values determine the direction of a slip, and obviously as we increase the load, the slip happens in one crystal, and further increase in the load happens in another one, and as we increase the load further and further, many of these crystals yield and the material yields as well.